So we have been talking about virtual memory module, right? And we will have a brief discussion on file systems and file management as well. Okay, so that will be for the next session. Okay, so we'll have all the topics that we have discussed as part of this course in final exam. I have posted some information regarding the dates when the final exam will be open. So it's going to be a comprehensive exam. Okay, um, and the test format will be approximately similar to what we had for the two midterm exams. Okay, and um, do you have any questions regarding that one? Okay. We have the last homework due tomorrow. Okay. Let me know if you want an extra day, and you should be able to submit by end of Thursday if you want. Okay. But for now, the deadline is in fact set to tomorrow night, which is Wednesday midnight. Okay. And that's all regarding the various tasks. We will not have any additional quizzes or homeworks past this. Okay. Um, and uh, uh, do you have any questions there? Okay. So okay, I guess that is I guess it's all fine. Right? So let's continue with what we have been discussing in the previous session. Okay, so we were talking about virtual memory, and in the previous sessions we discussed the concepts of demand paging and how it can be implemented as part of the page table and so on. Right? And we discussed the concepts of page fault and how what is the impact of a page fault on the overall performance, or in other words, to be specific, what is the impact of page fault on the average page access time for a given process? So we discussed those different concepts, and we have observed that the it is recommended to have as less um, number of page faults as possible. And towards that, we have discussed some of the optimization as well, some of the best practices to follow so that we can reduce the impact of demand paging. Okay? Um, and and then we discussed the concept of and then we discussed the concept of page replacement. What is its impact? Okay, and what is it that we can do when we do not have a free frame available whenever a page is requested, or whenever the requested page is not available in main memory, right? So as part of that, uh, we have discussed a couple of best practices again, and we discussed the overall approach for page replacement. And, uh, and as part of that, we have also discussed several approaches to identify one of the victim frames which need to be replaced in a situation when we do not have a free frame available which can accommodate the incoming frame, or the page that is being brought in from the backend store. Okay? So one such approach is the first in first out algorithm, where we keep track of the sequence in which the pages are brought into main memory, and whenever we do not have a free frame available to place an arriving page, what we do is we identify the first frame that is placed in one of these frames, and we swap it out. We save it back to the backing store, and then release that physical frame, and identify and allow the newly arriving page to be placed in that particular frame, memory frame. Okay? So that is that is in brief the approach taken by this FIFO algorithm. Okay. As you can see here, the FIFO approach, it is pretty simple to implement. We should be able to simply implement it using a queue, a FIFO queue. Okay. And so it is simpler to understand. It's a simpler concept, simpler to understand, and simple to implement as well. But it suffers from what we call the Belletti's anomaly, or in other words, uh, what this says is this particular approach. It does not it it it, it sometimes, depending on the kind of the sequence of page references, as well as depending on the number of frames that we have available, it it may not be the case that as if we provide more number of memory frames to a particular process, then it may or may not result in lesser number of page faults. Okay? So, or in other words, this particular approach of page replacement, it may not make best use of the additional memory frames that are provided to it in reducing the number of page faults. So that's the concept of Belletti's anomaly, and that is one of the drawback with this FIFO approach. Okay, uh, and uh, and then we discussed what we call the optimal algorithm. So optimal algorithm is the one which is which is as you can see from the term itself, which is optimal and not a practical approach. So what this approach suggests is we look into the future and identify a page to be replaced, which may not be used or referenced by the process at a later point in time. Okay, so we pick the one which the process is not going to use for the maximum amount of time in future. Okay? Uh, so by doing that, of course, we are reducing the number of page faults as much as possible. So so from that so based on that particular idea, we can say that this approach, it results in optimal number of page faults, or the least number of page faults possible for a given string of references or a sequence of references and a given number of given number of memory frames for a given process. Okay? So as you said, this is just an this is the um, optimal approach, or more like a conceptual approach, because we cannot really have we cannot really predict the pages that are referenced um, by a particular process, okay? Anytime in the future. So because it all depends on the kind of input that we have, and it depends on several other aspects as well. Uh, it all depends on the kind of it it, uh, it depends on of course it depends on number of frames that it has available and so on. So 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 for that reason, what we can do is, considering that this particular approach results in the optimal number of page faults, or optimal page fault count, we should be able to use it as a reference to measure how well some other algorithm performs, or how worse some other approaches. For example, how worse the FIFO approach is as compared to this one. Okay, so we should be able to use this as a benchmark to identify what is the least number of page faults that can occur given a process references a sequence of pages references pages in a specific sequence, and given some number of memory frames to the process. And an approximation the optimal algorithm is the least recently used approach, where instead of expecting the process to provide the future references, future page reference information, what we can do is we should be able to the approximate that information by using the historical page accesses by the same process. Or in other words, what we do is whenever we want to replace a page which is already in memory to accommodate a newly arriving page, what we can do is instead of looking into future as to how far in future that a particular page which is already in memory is going to be used, what we can do is we should be able to look back in the history and see when is the latest that page is already accessed, that a page is accessed in memory. And here, this approach, the least recently used approach, it depends on it depends on an assumption that the page which is recently used has higher probability of getting reused or re-accessed by the process as compared to a page which was accessed a lot earlier, a lot earlier. Okay? So so as you can see here, we have for the same reference string or for the same sequence of page references and for the same number of frames, this approach, the least recently used approach, it performed better than the FIFO approach, which resulted in 15 page faults. And of course, it is definitely less than it performed less than the optimal algorithm, which resulted in 9 page faults, as we have seen in the previous example. Okay? So here, as you can see here, this particular algorithm, least recently used algorithm, it resulted in 12 page faults. Okay? So overall, this approach, LRU approach, it performed better than, in general, it performs better than the FIFO approach. And another advantage is that it does not suffer from the Belladis anomaly as the FIFO approach does. So whenever we want to, an obvious consequence of that advantage is that whenever we want to reduce the number of page faults, we should be able to increase the number of frames that are allocated to the process, and thereby we can be guaranteed that the page fault for the same set of references, as we increase the number of frames, the number of page faults would either remain the same or they may even reduce. Okay? And that is the kind of guarantee that we have with the least recently used approach, which we do not get from the FIFO approach because it suffers from the Belladis anomaly. Okay? So for that reason, this is a practical approach and it is frequently used as well in modern operating systems. Okay? However, the implementation of this approach is not as straightforward as the FIFO approach. So here we have two different approaches that we can take to implement the least recently used approach. One of them is counter-based and the other one is stack-based. Or what we can do is each time a page is referenced, what we can do is we should be able to increase the counter for each page which is already in memory and assign the counter as 0 for the newly arriving page. Okay? So that way, whenever we want to replace a page, whenever we want to identify a victim page which is already in memory, we should be able to simply pick the one. We should be able to, in fact, go over the entire list of pages in memory and see which of those pages has the highest counter value, or in other words, which is the one which is not used recently. So, and we should be able to simply replace that page with the newly arriving page. Okay? So that is the counter-based implementation. And then we have what we call the stack-based implementation, where whenever the reference page, which is already in memory, what we do is we take we move that page to top of the stack, okay? And we move that page to top of the stack. Otherwise, if there is any newly arriving page, then again we place that page on top of the stack. And with the stack-based approach, whenever we want to identify a victim page to be moved out of main memory, we should be able to simply replace the simply remove the page which is at bottom of the stack. Okay, so in that particular manner, we the overall impact, the it is in fact easier to identify the victim page. We do not really need to go over the entire list of pages that we have in memory that are allocated to a process. But the overhead, but there is an overhead here, because we need to modify the stack contents by replacing one of the pages whenever a page is accessed. Okay, even though there is no, even though a page is not really replaced, we still need to modify the contents of stack for every memory reference or every page access, because we are going to identify that page in the stack and move it to top of the stack. Okay, so that's one of the overheads associated with the stack-based implementation. Okay, so these are different ways of these are two different ways of implementing this LRU approach. Okay, do we have any questions here? Okay, so now that we have seen now that we have seen that there is a there is a lot of overhead involved when we need to whenever we have to replace a particular page. So as part of that, to reduce the overall impact of page replacement, or in terms of overhead, here we have some of the optimizations that we can follow. One of them is, of course, as part of page replacement, there is page replacement. We have several individual tasks that we need to perform. One of them is identifying the victim frame, swapping out the victim frame, moving, or in other words, moving it to the backing store, and then releasing its frame so that the newly arriving page can be allocated that memory frame. Right. So to reduce all that additional overhead during runtime, what we can do is, or what the operating system can do is, it should be able to maintain some free frames. It should be able to maintain a pool of free frames, such that whenever a page needs to be brought in, one of these free frames can be allocated to the process, so that the new page can be accommodated there. Okay? So towards this, what the operating system does is, at regular intervals, it it scans the entire memory, or it scans the entire set of frames which are allocated to each process, and it identifies which of those frames are, are can be the can be replaced. Okay? Or to be specific, what it does is, it goes through each of those it goes through each of the memory frames, and it goes through each of those pages which are already in memory, and sees which of them are dirty pages, or in other words, the pages that are modified in memory but are not yet written to the backing store. Okay? So it identifies such dirty pages and proactively performs the write in background. It performs the write of those dirty pages or modified pages, and marks them as um, as uh, not and it in fact um, removes the dirty bit on those pages. Okay? So that whenever at any point in time, eventually in future, whenever a victim page needs to be identified, uh, to whenever a victim page needs to be identified, we should be able to simply uh, simply select one of those frames, one of those pages which one of those pages which do not have the dirty bit marked, and we should be able to simply discard the content, and we should be able to simply make use of that memory frame to accommodate the new page, newly arriving page. Okay? Or what the operating system can do is, in fact, it can simply go ahead and discard the content as well, and keep them, keep all such frames as part of the pool of free frames, so that one of these free frames can be directly allocated. Okay? Um, and another optimization is, as part of keeping these pool of free frames, what the operating system can do is, it it performs the write of those pages into the backing store and marks them as a free frame that is available. But at the same time, it also maintains the contents of that particular frame intact, and it maintains the information regarding what page was loaded in that particular frame. Okay? So that at some point in time, later on, let's say we have already written this contents of a particular page back to the backing store, and then we have marked it as a free frame. But considering the contents of the page are still physically available in main memory, the next time when that page is referenced, we already have the contents in one of these free frames. So we do not really need to fetch it from the backing store. Okay, so that is another optimization that we can have. Uh, so these are some of the best practices, or some of the optimizations that we can have to reduce the impact of page faults at runtime. And there may be a situation sometimes that it's not that the applications themselves, they may have better understanding uh, regarding the page accesses made by the application itself. For example, we have database environments which may perform some kind of pre-paging, okay, where it predicts that where it predicts what pages may be accessed by the database environment, and it fetches, or it requests those pages to be brought in from the backing store into the main memory ahead of time, before the actual page reference itself is made, so that whenever the page reference is made by the database, or the corresponding application, we already have the required page in memory, so it will be an in-memory access rather than a page fault. Okay, so for that reason, there may be, um, instead of the operating system making the decision regarding which pages need to be buffered in memory, or which pages need to be brought in ahead of time, what we can do is, instead of doing that, for some specific type of applications like databases, we should be able to allow the applications themselves manage the available manage the corresponding memory by themselves. Um, so by doing that, we refer to that one as being in raw disk mode, where where the applications themselves are allowed to manage a part of the memory by themselves, and of course it avoids it avoids this kind of situation, where where we have the operating system brings in some pages from the disk, and 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 the pages that are brought in by the operating system as part of, say, pre-paging, that those pages may be again swapped out by the databases based on their knowledge of based on their prediction of pages which will be used by the application. Okay? So so if that is the case, then the kind of effort that is put in by the operating system in pre-paging or swapping in some of the pages from the backing store, that will be that that will be a wasted effort. Okay? Or in other words, what we refer to that as double buffering. Okay? So this leads to wasted effort, and this can be avoided by allowing the by allowing some of these applications like databases to manage their own memory allocations. Okay? So so this is another optimization that can be followed. So 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 far we have been talking about a situation where we have allocated some number of memory frames to a particular process, okay? And whenever there is a need whenever there is a need um, for a new page, then we have discussed how one of the frames, how one of the pages that we already have can be identified for replacement. Okay? Um, but it may there's uh, but as we do it, of course, we want to consider what is the minimum number of pages, or what is the number of what is the minimum number of frames that a particular process need to be allocated so that it can perform so that it can continue with the program execution. So as part of that, we have two different allocation schemes here. One of them is fixed allocation, and the other one is priority allocation. Um, so, and then, of course, there are a couple other approaches as well. So um, a simple approach would be what we call the fixed allocation. Okay? Or in other words, let's say we have some n number of processes, active processes in the system, and we have some m number of frames. Then what we can do is we should be able to allocate an equal number of frames to each of these processes. Okay? Say, for example, if we have about 100 memory frames, or let's say we have the entire memory partitioned into, say, 100 number of frames, and if we have 5 active processes in the system, then based on equal allocation method, we should be able to allocate 100 by 5 equals about 20 frames per process. Okay? And at the same time, we should be able to maintain some of the frames in as a free buffer pool, okay, so that we can allow fast page replacement. So this is definitely one simple approach, but then clearly it is not sufficient, right? Because it may be the case that even though we have these many number of processes, all the processes may not really have similar memory requirements, or in other words, they may not be of the same size. Okay? So one improvement based on this one would be allocating the number of frames to the each process based on their respective memory needs. Okay, so what we can do is we should be able to um, allocate the number of frames proportionate to the size of each process. Okay? So accordingly, if we have some process with large memory needs, then it will be allocated more number of frames as compared to the one which needs less number of frames. Okay? So that is another approach, and So that is another approach. And as we can see here, this is, as we can see here, considering that the number of processes in a particular system, it may vary over a period of time as new processes are initiated and some of the processes are terminated, right? So for that reason, we should be able to accommodate this to support dynamism in the number of processes that we have in a system as well. Yeah. So so the number of frames that are allocated to each process, it may change dynamically depending on what set of process that are running at that specific point in time. Okay? So, so this is a more of a dynamic approach. Um, okay, so once we have these, once we assume that once we allocate some number of frames to each process, naturally, the next question is what happens when we have to perform a replacement? So whenever we have to perform a replacement, again, we have two different approaches. One of them is global replacement, and another one is local replacement, where uh, where we what we can do is whenever we have to whenever we are making use whenever a particular process is making use of all the frames that are allocated to the process, and if it needs to um, if it requests another page which needs to be brought in from the backing store, then what we can do is one option is to identify a victim frame from a victim page from the pages that belong to the same process. Okay, so so by doing that, what we can do is we should be able to um, we are in fact making decision regarding page replacement uh, based on based on the based on the page access behavior or the reference string that belongs to the same process. So for that reason, uh, multiple runs of the process of the same program, given the same number of memory frames allocated to it, that will result in consistent performance of the process. Okay, it will always result in the same number of page faults, considering considering we have the same reference string or the sequence of page references as well as the number of frames allocated to the process. Okay. So local replacement policy, it results in consistent performance of the process, but at the same time, it may result in underutilized memory, considering it may result in underutilized memory considering we are allocating some number of frames to each process, but there may be a situation that some of the pages which are already loaded in memory, they may not be accessed as much. Okay? If they are not being actively utilized, um, then they may continue to stay in main memory even though they are not currently being accessed. So, so that may result in underutilization of memory space that is allocated to the process. Okay? And otherwise, uh, instead of that, what we can do is we can allocate those memory frames which are not being utilized by the process uh, by some other process by some other process which is in need of some additional pages, or in other words, by those underutilized um, frames allocated to a process can better be utilized by some other process which is experiencing high page fault in the system if we allow some other process to make use of it, or in other words, if we allow global replacement. Okay? So what global replacement policy suggests is whenever we want to identify uh, whenever we want to identify a victim page to be replaced with one of the arriving page, we should be able to look for or identify the victim page not from the pages that belong to the same process, but any of the pages that are currently loaded in memory that belongs to any other active process as well. So that is the global replacement policy. And clearly, with the global replacement policy, we a particular process, it does not really have control regarding what pages are kept in main memory and what pages are not available in main memory. Okay, so for that reason, uh, the overall process execution of the overall runtime of the process, it may be impacted by not just by the page references made by the process itself, but it may be impacted, the runtime of a process, it may be impacted by the set of processes which are currently running on the same system. Okay? Um, and of course, it depends on the kind of accesses that are made by other processes as well. Okay? So for that reason, the runtime of a process, it may vary greatly and it may not be consistent. Okay? But but considering that whenever we want to make a decision regarding which page can be a victim page to support to allow replacement to allow the to accommodate a new arriving page, uh, we should be able to make a better decision based on which of the pages are currently being utilized by their respective process. Yeah, and thereby the overall performance of the system is improved. Okay? Because we are making best use of the entire available physical memory. Okay? And for that reason, in spite of in spite of this global replacement policy resulting in unpredictable execution times of the processes, it is more commonly used in modern operating systems. Okay? So, so these are two different page replacement policies, and clearly, as we can see here, if we have local replacement policy implemented, then each process, it continues to have the number of memory frames allocated to it at all the times, as long as the uh, process is executed. Okay? Whereas when we implement the global replacement policy, naturally the number of frames that are allocated to a process, to each process, it may vary over the execution of the process itself. Okay? So that is one other aspect that we may want to consider and be aware of. Okay, so these are the two different policies, replacement or reallocation policies. Do we have any questions here? Okay, moving to the next one. Here we have now that we have been talking about uh, the page replacement and as part of that we have discussed that one of the optimizations is to maintain a pool of free frames such that whenever a need arises, we already have a free frame that can be made use of. Okay? And that in fact reduces the amount of overhead resulting from a page fault. Okay? So what the operating system can do is to maintain a number of page faults, to maintain the number of free frames. What it can do is it should be able to go over the available pages that we have in memory, and it should be able to perform a write of the dirty pages back to the packing store and mark them as frames belonging to the free pool of free frames, so that one of those free frames can be made use of. Okay? Uh, so that is one tasks performed by the operating system. But one of the drawbacks with that particular approach is as we is we are in fact making is that the operating system itself is proactively performing the right operations of the pages which are already written or dirty, right? And there may be a situation where where the respective pages may be accessed right away, and they are currently in use. And if the operating system performs these proactive writes, there may be a lot of unnecessary writes which are in fact going on. Right? So there is an additional overhead that goes on that there is an additional overhead on the system. Yeah, reserved from all these unnecessary or early writes that are being performed by the operating system. Okay? So for that reason, what for that reason we need some kind of a trade-off there as to how many how many pages can be written to the how many pages can be written early to the backing store and be maintained as part of the free pool of uh, as part of the pool of free pages, okay? Free frames. So so regarding that, um, what the operating system does is whenever the number of here is one approach that is taken. Okay? Whenever the number of frames in the free pool is below the minimum threshold, what the operating system does is uh, it starts releasing some of the it starts performing the writes, and it starts releasing some of the memory frames and include them as part of the pool of free frames so that they can be used. And it performs that until there is some maximum number of until this maximum threshold is reached, and we have so many number of free frames available. Okay? And at that point it will simply stop reclaiming the pages. Okay? Or in other words, it will stop writing the pages to the backing store and releasing the corresponding releasing the respective frames. Okay? It will continue at that point, and then later on, it will simply it will simply pause reclaiming the pages. It will simply wait until the number of free frames again falls below to some below the minimum threshold, at which point again it will initiate the process of reclaiming some of the frames in memory. Okay? So this is by ensuring that we have so many number of free frames, the overall impact of page faults that happen that can be reduced by ensuring that there is at least some number of free frames available in the system which can be used to serve the page faults. Okay? So the exact and of course the exact numbers of these minimum and maximum thresholds, it depends on the system implementation. Okay? Okay. So this is again one of the optimization that is followed as part of the operating systems, the modern operating systems, okay, to ensure that there is always some free memory frames available to satisfy any of the newly arriving requests. Um, now, now here is another concept that is of our interest. Um, so what happens is whenever a particular process um, whenever we allocate some a number of pages to a particular process, if the number of pages that is allocated to a process, if it is not sufficient, then as the process continues its execution, it it keeps requesting same set of pages. The pages that are currently in use will be swapped out to accommodate to accommodate some other pages, right? So for that reason, um, so that in fact results in high page fault rate, because the process would be requesting the pages which are recently swapped out, right? And thereby, because of the high page fault rate, of course, it results in low utilization of the processor itself, because a lot of work is being done in simply swapping in and swapping out of the pages of the same pages, right? And so this is a special situation where considering that the processor itself is not being utilized um, uh, to an optimal extent, the operating system may assume that the reason for low CPU utilization is because there are not enough active processes available in main memory. Okay? And it acts by and it attempts to improve the overall processor utilization by adding more processes, or by, in other words, by moving one of the processes from the backing store and making it active and adding it to the ready queue. Okay? So, or in other words, what the operating system does is it allocates some it allocates some number of frames to a newly arriving process, and thereby we have another process which is also under execution, and which again may request some additional memory frames as part of its execution. Okay? That uh, that may again increase the number of page faults in the system. Okay? So um, so this kind of a situation where the operating system would where the operating system would simply assume that there is a less number of processes, and it keeps adding more and more processes, and all these processes, they continue to perform they continue to um, experience high page fault rates, because there is not a sufficient number of memory frames that can be allocated to each of these processes. So that situation, we refer to it as thrashing. Okay? Or in other words, there may be a situation where as we increase the number of active processes in the system, to some extent the CPU utilization also increases. But at some point in time, the all these processes, they do not have sufficient number of free memory frames available, which results in high number of page faults, and the system is spending a lot of time in performing these swap in and swap out of the pages, or uh, uh, and thereby the CPU itself is not utilized in an appropriate manner. Yeah. Um, so this is this kind of situation we refer to it as thrashing. Okay? Uh, Thrashing, of course, it results in low CPU utilization, and which is something what we want to avoid. Okay? So so this is definitely a problem. Um, so now to to resolve this problem of thrashing, we want to identify what is the number of frames that is least required, what is the least number of memory frames that is required by each of the processes, depending on the kind of task that is being performed by the process itself. Okay? Depending on the nature of the process itself. Okay? So, so that is an important factor to identify least number of what is the least number of memory frames that is required to accommodate all the pages that is required by a particular process. Okay? And we want to do that for each process that is active in the system. Okay? So um, if we can, that is in fact referred as the locality of a process, or in other words, the set of pages that a particular process needs for its current execution. Okay? If we do not have all the pages that a particular process needs as part of its current execution, what it does is it naturally results in additional page faults. Okay? So so we need to ensure that we have the entire locality of a process at any given point in time is available in main memory. Okay? And we want to ensure that we want to ensure that for all the processes that we have currently active in the system. Okay? So for that reason, we want to ensure that we want to ensure that the sum of the localities of all the active processes we to be uh, to be less than the overall memory size, or in other words, we should be able to accommodate the locality of all the active processes in main memory. And if we cannot do that, or in other words, if we cannot accommodate the entire locality of each active process in our main memory, then that would result in this crashing situation where the process do not have sufficient memory frames allocated, and thereby they continuously result in they result they request the pages which have been recently swapped out. Okay, so um, okay, so here we have a picture that shows for a specific application, for an application or a process. It shows over the execution of the process what are the different memory locations that are accessed by the process itself. So as you can see here, the different memory locations that are accessed by a process over a period of time, they 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 belong to the they are located pretty closely in the memory. And for that reason, the immediate references to specific locations, to specific logical addresses of the process, um, over time they belong to either the same page or to the pages which are located nearby. Okay, that is one aspect. Another aspect is the various addresses that are the various logical addresses that are referenced by a particular process. They belong to the pages. They belong to the same set of pages over a period of over a brief period of time. Okay, so for that reason, if we can ensure that the corresponding pages which are referenced, if they are loaded and available in memory, we should be the future references will be the future references by the process, they can be served directly from the pages that are already loaded in memory, rather than resulting in page faults wherein we need to bring in another page from the backend store. Okay, so that is what we can see here. If you just see here, we have the page numbers 18, 19, 20, 21, 22, and so on, right? And in each of these pages, we have a small block of addresses here. And over a period of time, a particular process will be requesting, um, or over a period of time, the logical address referenced by the process, it is marked by a dot here. Okay, so from this we can see that from here until here, the process is making use of the pages, the content in the pages from 18 through 24. Okay, so from this we can see that there is a need for the process to have all these different pages from 18 through 24 in memory as part of its execution. Okay? And for that reason, we need the respective number of frames allocated to this process at that point in during that period of its execution, from here up through here. Okay? And if we for whatever reason, if we allocate lesser number of frames, what it does is, as the process as the process executes during this period of time, the first part, it it if we allocate lesser number of frames, there may be a situation where a page is swapped out to accommodate another page, okay? And immediately in near future, the swapped out page is again referenced, and that would again result in a page fault. Okay, so for that reason, this is in fact referred as the locality of the process, and and it is recommended that the entire locality of a process is loaded and available in memory during the execution of the process. And if we can do that, it will definitely, it will drastically reduce the number of page faults. Um, and one other important aspect here is, as the execution of of the process progresses, the locality itself changes over a period of time. So if you see here, from this point to until this point, the process is accessing these pages 18 through 24, as well as 29 through 30, and then 31 through 33 to 34. Right? So these are the pages which are primarily being accessed. Whereas as the process moves to the next stage, it is accessing this set of pages more and this set of pages more. Okay? And as it moves to the end, it is in fact accessing this set of pages more as compared to any other pages. Okay, so the locality has in fact shifted from this set of pages to this set of pages, or in other words, this set of pages instead of this set of pages here. Okay, so that is one important thing that we want to that we may want to be aware of. Okay? So as long as we can accommodate the entire locality of a particular process, then we should be able to reduce the chances of crashing, and we should be able to, of course, reduce the number of page faults as well. Okay? Um, so the um, this set of so the entire locality of a particular process, we should be able to identify by using what we call the working set model. Okay? So working set model, using the working set model, what we can do is we should be able to we should be able to identify from the entire page references. We should be able to see we should be able to see which set of which set of pages are currently being accessed by the process, okay? Are currently being actively accessed by the process. Okay? So now if you see here, the working set size, it can be identified based on the different pages that are accessed by the process over a period of time. Okay? And that period of time, if we take it as too small, then of course we may not be able to identify the entire set of pages that it needs. For example, if we simply look at it from here through um, from this point through this point, for example, then we may not be able to actually identify that we have all these that we have these pages which are also being accessed. Okay? So I mean, if we just look at it from here through here, then it shows that these are the pages that are being accessed. Yeah? And if we consider the working set size to be too large, then there may be a situation where the working set may comprise multiple localities and not just one locality. For example, for example, if we consider it from this point through, let us say, this point, then here we have if we consider from this point to this point, then we see that the entire locality comprises the pages from 29 through 32, as well as from 24 through 18. But of these, if we see the pages from 30 through 32, they are not really being accessed until this point. Okay, so if we allocate the number of frames to support to have these pages 18 through 24 and 29 through 32 all along from this point to this point, then we will not be making use of the frames which are allocated to these pages in an efficient manner, because these pages are not referenced until this point in time. Okay? So in brief, if we consider the working set size to be too large, then it may comprise multiple localities, and thereby we and thereby the number of frames allocated to the process to accommodate that entire set of localities, it may not be um, it may not be efficiently being used by the process. Okay, so for that reason, we need to make a appropriate decision regarding the actual working set size of a particular process. And of course, if the working if the working set size of a process is if delta is set to infinity, or in other words, if we consider the entire time that the process is executed to identify all the set of pages which are accessed by the process, then of course it includes the entire entire process address space. It encompasses the entire program. Okay? So um, so that is one extreme situation. But considering considering these aspects, we need to ensure that the uh, the the time that we use to identify locality, or to identify the working set of a particular process is important. Okay? So here we have some examples where, let's say if we take delta to be of this particular size, then we see that it accesses all these different pages: 2, 6, 1, 5, and 7. So we have 5 different pages that that we that this particular process is accessing. Or in other words, if we consider delta to be this size, then we can say that the current locality of the process is these 5 pages. Okay? And similarly, at this point in time, the locality of the process is only 2 pages. It is only accessing these 2 pages, 3 and 4. Okay? Now, if we allocate 5 number of frames here, or 2 number of frames here at this point in time, then we should be able to accommodate the entire locality of the process. Okay? And from here through here, if we allocate 2 frames, then this process does not result in any additional page faults. Okay? So otherwise, if we allocate less than that, let's say we allocate only 1 frame to the process, then it will definitely result in multiple page faults here, from here through here. It results in 1, 2, 3, 4, and 5 number of page faults. Okay, so this is just one example to show how. This is one example to show um, how it is really important to ensure that we have the entire locality of a process address space, entire locality of a process at any given point in time loaded in memory, okay? To ensure that we have lesser number of page faults. Okay, and if we cannot, then of course it results in higher number of page faults, or in other words, it may result in crashing. Okay? And if we if we if we cannot accommodate the entire localities of or the working set size of each process, or collectively the working set size of all the active processes in the system, if we cannot, then it may result in crashing. And one solution to that one would be to to suspend or swap out one of the process, and then wait until one of the wait until the memory needs of the process reduce at some point in time, at which we should be able to swap in the process back, and we should be able to resume its execution. Um, so, so this is the working set model. Okay, and clearly this particular approach that we take here, it is a little difficult to implement because it is very specific uh, to the delta that we select. Okay, it depends on the working set size that we identify for each process. It depends on the time that we select, during which we, in fact, identify the set of pages that is required to be in memory. Okay, or in other words, it is dependent on this delta. Okay, which is not always practical. Hence, we have another approach based on the page fault frequency to identify if we have sufficient number of uh, pages allocated to a particular process. Okay? So with this particular approach, what we can do is if we, with this particular approach, what we can do is we increase the number of frames to a particular process and see how its page fault rate changes. Okay? Ideally, if the page replacement algorithm it ideally if it does not suffer from Belladis anomaly that we have discussed, um, if we increase the number of frames allocated to a process, the corresponding page fault rate of the process, either it remains the same or it may even reduce. Okay? So what we can do is we should be able to verify the change in page fault rate by increasing the number of frames allocated to the process, and and as long as we have as long as we have the page fault rate between um, as long as we have the page fault rate between some pre-specified upper bound and lower bound for a given process, it is fine. Otherwise, if we have a higher page fault rate than uh, uh, if we have a higher page fault rate than the upper bound, then what we can do is we can go ahead and add more frames to the process. Otherwise, if it is if the page fault rate is less than lower bound, then that means that we may not be efficiently making use of the number of frames which are already allocated to the process. So what we can do, we should be able to decrease some number of frames. Okay? So this is a more straightforward and simpler approach. Okay? However, with this one, we need to apply the local replacement policy because we are specifically allocating so many number of frames to a particular process. Okay? So that's regarding this one. And one simple one other aspect that we may want to consider is as as a process moves from one locality as part of its execution, as it moves from one locality to another locality, what happens is there may be a higher page fault that is observed because it is loading an entirely new set of pages. Once it has the entire set of pages that is required as part of that locality, there will not be, if we can accommodate the entire locality um, at that point in time, then the number of page faults would be reduced. They'll be minimal because the process already has all the required pages loaded in memory. Okay, and and note that as we have seen in the previous example as well, this working set actually changes over a period of time, over its execution. So for that reason, if we observe during the entire execution time of a process, if we observe the page fault rate, then the graph would look something like this, where the process is loading a locality and that resulting in a higher page fault rate briefly for a brief period of time, followed by a period of time when the page fault rate is pretty low. Okay? So, and from this, again, even from this particular graph, we should be able to identify what is the working set size of a process. Yeah? So a working set of a size of a working set of a process, it can be identified by using this a peak as well as a small valley after that. Yeah. So this can be observed from this picture as well, where the process is initially, if we can, there may be an initial peak of page faults at this point in time to load all these different pages. And once all these different pages are loaded, there will not be any page faults anymore, considering all these pages are already available in memory. So at this point in time, there will be a valley until this point, and at this point in time, there will be this a peak in page fault rate by the process to load all these different pages here. Okay? And once that is done, it will stay stable until this point when these pages are requested again. Okay? So so this kind of behavior can be observed from this picture. Okay? Any questions here? Okay, all these are different aspects that we may want to be aware of, and some optimizations that we can implement as part of the virtual memory management. Some techniques that are used to improve the performance of the system when we are using virtual memory. Okay, so so this concludes this module. As I mentioned earlier, we will briefly discuss the concept of file management and file systems in the next session. Let me know if there are any questions. Thank you.
Thank you.